Section 12.5 is about tangential and normal components of acceleration. Now, just think of a particle traveling in space. Now, we're considering that the particle is traveling along the x, y, and z axis. Now, if that is the case, then right now we're going to be talking about acceleration, how the particle is accelerating through space. Like in space, there are actually three components or three vectors acting on the acceleration process. One of them is called the what's called the tangent component, the normal component, and the binormal component, which basically it gives us an idea of the three different directions in which the vector is moving. So remember that the tangent vector, as we defined before, is represented by the derivative of the position with respect to the length of the curve, which is dr over ds. That will be the unit tangent vector. Okay. Also think of the basically the normal component. The normal component, we said it was 1 divided by what's called the curvature times the derivative of the tangent vector with respect to the arc length. And basically that tells us the normal vector, remember, goes in towards the circle of curvature of the particle at any given point. Okay. Now we're going to define one last vector, and we need to define it because now we're talking about a particle moving in space. So now we're going to have one that is called the binormal vector. The binormal vector is going to be a vector that is both normal to the normal and the tangent vector. Okay, so it's perpendicular to both of them. So you see it is going in the direction of basically my z or my k. Okay, so it's going to be normal to them. So these are the three forces or the three vectors acting on a particle as it moves in space. Okay. Now, how do we get a vector that is normal to any other two vectors? By doing the cross product that was introduced in section 11.4. Okay. When I do the cross product of these two vectors, that will give me the vector that is normal to these two, which is going to be what we call the binormal vector. What is special about these three vectors in conjunction is that they create what is called a Frenet or Frenet. Now, what is it called by the Frenet? It basically it tells us the path, the three paths in which the particle is traveling. Okay, and you see they're traveling in the direction of what we call like a cube, like if it was traveling along with a unit cube. Okay, now this cube, there are three important faces in the cube which we call planes that we're also going to be talking about. We have the plane that goes along the tangent vector. That plane, we call it the rectifying plane. Then we have the plane that goes along with the normal vector. That one, we call it the normal plane. And then we have the plane that basically is normal to the binormal vector, and it's basically like the base of that cube. That base, we call it the oscillating plane. And they're introduced on the next page. So when the particle is traveling in space, like I said, the plane that goes along with the tangent vector as the particle is going is called the rectifying plane. Okay, it goes with the tangent vector. In other words, it is perpendicular to the normal vector. It tells you right here. Then we also have the normal plane. The normal plane goes with the normal vector, and that basically is perpendicular to the tangent vector. So that we call it the normal plane. And the last one is the oscillating plane. That one goes it is the plane between the tangent and the normal vector formed by them, and that is perpendicular to the binormal vector. So that's the osculating plane. Okay. We're going to be finding equations of planes before, so remember that since the rectifying plane is perpendicular to the normal vector, then the components of the normal vector will be the ABC components of this plane. Okay. Since the normal plane is perpendicular to the tangent vector, then the components of the tangent vector will be the A, B, and C components of the normal plane. And the same thing happens with the osculating plane. Since the binormal vector is perpendicular to the osculating plane, then the components of the binormal vector will be the components of the ABC components of the osculating plane. We're going to talk about that later in the section. Now we're going to be talking about acceleration. Okay, a particle accelerating, the motion of the particle accelerating along a path. So one thing is that let's keep in mind that velocity of a particle is given by the derivative of the position with respect to time. But if we're talking about a particle, let's use what is called the chain rule to do the derivative with respect to basically when we have, for example, if we have the particle in terms of the arc length and not with respect to the parameter t, that would be the same as the derivative of the position with respect to the arc length times the derivative of the arc length with respect to the parameter t. Okay, but what do we know? We know that the derivative of the arc of the position with respect to the arc length, we already defined it, that is the same as the unit tangent vector. So then we have the derivative of the unit tangent, the unit tangent vector times the derivative of the arc length with respect to the parameter t. But now, what if we want to talk about acceleration. Acceleration is the derivative of the velocity. So looking at both sides of this equation, we're going to get the derivative of this side and this side to get the acceleration. So the derivative of the velocity is the acceleration, and now we're going to look at the derivative of this guy with respect to t. Okay? So if I get the derivative with respect to t of that guy, what are we going to get? So if I get the derivative with respect to t of the tangent vector times the derivative of the arc length with respect to t, then we're going to use the product rule right here, because this is a product. So it would be t times the derivative of this guy, the derivative of the arc length with respect to t. Since it is already the derivative, then it will be the second derivative of the arc length with respect to t squared times the tangent vector, plus now the second times the derivative of the first, so it will be the derivative of the arc length with respect to t times the derivative of the tangent with respect to t. So far so good, that's what we have. Okay, so we already have one of the components. So this is called the tangential component of acceleration. What does that mean? Tangential component, so look at the picture on the right. So when a particle is accelerating, so the acceleration, you see that it's going to have two components, a tangential component and a normal component. So first of all, let's talk about this guy. This is the tangential component that you see right here. And that is the one that goes tangent to the curve at any given point on the curve, in this case at this point P. So that's called the tangential component of acceleration. Okay. Now, what about the normal component of acceleration? That will be given by the second part. Okay. So, well, finishing with the tangential component. So you see that to find the tangential component of acceleration, we need to multiply, which is basically this, the second derivative of the arc length with respect to the t squared times the tangent vector. Now the unit tangent vector. So this the second derivative of the arc length with respect to t is what we call the tangential component of acceleration. That tangential component of acceleration, since it is the second derivative of the arc length with respect to t, it is the exact same thing as the derivative of the speed. The derivative of the speed, or the derivative of the magnitude of the velocity. Okay, because we're talking about arc length. Okay. Now, let's talk about the normal component, which is going to be given by this guy. Now, this guy, you see that this one tells me, this one we're not done yet, because right here the tangent is with respect to t. But now the derivative of the tangent, but remember, we're thinking of the particle being in terms of its arc length. So let's use the chain rule on this guy as well. So we can write it as the derivative of the tangent with respect to the arc length s times the derivative of the arc length s with respect to t. That would be the same thing. So this is what you see right here now. So, and then if I get the derivative of this guy, then let's just remember that the derivative of the tangent with respect to the arc length, that was the same thing as the what's called the curvature times the unit normal vector that was defined on the previous section. Okay, so that's the same as the curvature times the unit normal vector. Okay, and then the derivative of the arc length with respect to t times the derivative of the arc length with respect to t, it is the same as the derivative of the arc length with respect to t, but squared. But the derivative of the arc length with respect to t is the same thing as the magnitude of the velocity squared. That's what you see right there. So, and that gives us what is called the normal component of the acceleration. Okay, that will be the normal component of the acceleration. This right here. Okay, so that would be the normal component of acceleration would be the same as the what's called the curvature times the magnitude of the velocity squared. Okay, so this gives us another way of writing the acceleration of a particle without having to find the tangent, unit tangent vector and the unit normal vector, which you know by experience from the previous section, it takes a really long time to do. So we're just going to write the acceleration in this section so that we can save time in terms of t, a scalar component times the unit tangent vector, plus a scalar component times the unit normal vector. Because those are basically the only two forces that will be acting on the acceleration process. You see that we have this tangent and we have this normal. When we get the magnitude, the resultant magnitude, that gives you this yellow A, which is basically what we call the acceleration of the particle at any given point along the curve. So it is basically, you see that right here, it is starting to decelerate, accelerate less until it gets to this point, which there is no acceleration, right? So those are the things that we're going to consider now. So one last thing that I forgot to mention. This creates a right triangle right here. So another way of looking at the acceleration is using the Pythagorean theorem, because this is going to be the same as the the tangential component of acceleration plus the what is called the normal component of acceleration equals to the acceleration squared. So I'm just going to put it like this. The tangential component of acceleration squared plus the normal component of acceleration squared equals to the acceleration of the particle squared, which is the same thing as the acceleration being equal to the square root of the tangential component of the acceleration squared plus the normal component of the acceleration squared. And that's the formula that we have defined right here. Well, in this case, it is solved for the normal component of acceleration. but we can utilize it in any way to find any of the components. If I know the acceleration and the normal and the tangent component of acceleration, then I can find the normal component of acceleration by just using Pythagorean theorem. Because they create a right triangle, the tangential component of acceleration and the normal component of acceleration. All right. So, let's start with this question. I want you to write A in the form the ATT plus ANN, which is the scalar component of the tangential component of acceleration times the unit tangent plus the normal component of acceleration times the unit normal. Okay, instead of without finding the t and the n, which takes us a long time. Okay, so first thing that we need to do to be able to find those components, let's recall, these are the things that we need. We need the derivative of the position, and then we get the magnitude, of course, and then we need to get the derivative of the velocity, because the derivative of the velocity would be the tangential component of acceleration. Okay, so let's find that guy first. So let's find the derivative right here. The derivative of y is just a constant, and right here y is just a constant. The derivative of cosine will be negative sine, so it would be negative y sine of t I plus, and the derivative of sine would be cosine, so it would be y cosine of t j, and the derivative of t, zt, it would just be z plus zk. Okay, then we need to get the magnitude. Okay, remember that this is the same as the velocity, right? So now we need to get the magnitude of the velocity. So that will be the square root of, square this component, it would be y squared times sine square of t plus y squared times cosine square of t, and then square this component, so it would be plus z squared. But then if I factor the y squared, look at what's going to happen. You're left with sine square of t plus cosine square of t, and then plus z squared. And what do you know? Sine squared plus cosine squared equals 1. So that leaves me with y squared times 1, which is y squared, plus z squared. So that would be the square root of y squared plus z squared. Y is a constant and z is just a constant. They're just constants in this vector moving in space. So what would happen if I get, remember now I need to get the tangential component of acceleration. Okay, I'm going to find the tangential component of acceleration, and that is the same as the derivative with respect to t, with respect to the parameter t of the magnitude of the velocity. But if I get the derivative with respect to t of the square root of y squared plus z squared, knowing that y and z are just constants, so this is just a constant basically, the derivative of a constant will always be equal to 0. Okay, so what next? Now we can probably get the acceleration. I think since this is the velocity, I think we can get the acceleration. Because the acceleration, it is the derivative of the velocity, right? So that's what we're going to do next. A sub t, which is the derivative with respect to t of the velocity. Okay? So we're going to get the derivative of the velocity, which is going to be this guy. The derivative of negative y sine of t would be just negative y cosine of t, because y is just a constant, I. The derivative of y cosine of t would be negative y sine of t, and that's j, and the y is just a constant, and the derivative of the constant z would just be 0k. Okay, so then I'm going to get the magnitude of the acceleration. Okay, I'm going to get the magnitude of the acceleration, because then to find the normal component of acceleration, guess what? I'm going to use the formula, the Pythagorean theorem formula that I introduced. Okay, so let's get the magnitude of the acceleration. So it will be equal to the square root of the first component square. If I square it, it would be y squared cosine square of t, plus the second component square, which will be y squared sine square of t, plus the 0 square, which is going to be 0, right? So then if I factor the y squared, I'm going to be left with y squared times sine square of t, plus cosine square of t, but sine square of t plus cosine square of t is equal to 1. 1 times y squared is going to be y squared, and the square root of y squared is just going to be y. So the acceleration, the magnitude of the acceleration, or it is accelerating by y units, okay, whatever y is. So that's the acceleration of a particle at any point in space. So now if I want to find the normal component of acceleration, that's the last thing we need to do. That will be the Pythagorean theorem. Remember, this is my hypotenuse, basically, the acceleration. The tangential component is one of the legs of the triangle. So the formula, it is the magnitude of the acceleration minus the magnitude of the tangential component of acceleration, both of them squares. So the normal component of acceleration equals to the magnitude of the acceleration squared, which is y squared, minus the tangential component of acceleration. The tangential component is 0 squared, so that would be the square root of y squared, which is just going to be y. That's the normal component of acceleration. So what is the acceleration of this particle in space? The acceleration can be written as the tangential component of acceleration times the tangent unit tangent vector, plus the normal component of acceleration times the normal unit vector. So that would be the tangential component of acceleration is 0 times the tangent unit vector, plus the normal component of acceleration is y times the normal unit vector. So this will be the acceleration of the particle without having to find the unit tangent or the unit normal. Just keep one thing in mind that I forgot to mention is that when you get the square root, since this is a constant in terms of a variable, we need to make sure it's positive, right? Because the square root right here must be a positive value, right? So I'm just going to put it in absolute value just to avoid this constant being a negative. Okay. So, and that concludes this question. Again, we can always find the tangential component of acceleration and the normal component of acceleration. The tangent, unit tangent, and the unit normal, and multiply times these scalars, and that's going to give us the acceleration. But remember, if we do the acceleration by the normal way, get the derivative of the position, then get its magnitude, divide the derivative of the position by the magnitude, then that's the tangent. Then get the derivative of the tangent, then get the magnitude, divide the derivative of the tangent by its magnitude, that's the normal. And basically that normal, then from there we can get the acceleration, but again, that's, you know, a long way and a long work to get to this answer. Okay? It would just be the absolute value of the constant y times the unit normal vector. That will be the exact same value, like the exact same function for the acceleration. Okay. All right, so that's all we needed to find. Yeah. Next, let's do the same thing here. I want you to write A in the form A equals a scalar component of the tangent times the unit tangent plus the scalar component of the normal times the unit normal. Okay, without even finding t, the unit tangent or the unit normal. We're just going to write it in this format. Okay, so we need to find the velocity first of all, which is the same thing as the derivative of this position. So the derivative of 3t plus 2 would be 3i. The derivative of 2tj would be 2j, and the derivative of 3t squared k would be 6tk. Okay. Now we need to get the magnitude of the velocity. And the magnitude of the velocity would be the square root of 3 squared, which is 9, plus 2 squared, which is 4, plus 6t squared, which is 36t squared. And that gives us the square root of 13 plus 36t squared. Then we need to get the scalar component of the tangential component of acceleration. We need to get the derivative with respect to t of the magnitude of the velocity. Okay, so in other words, we need to get the derivative with respect to t of this guy. I'm going to put it as a 1/2 instead of the 13 plus 36t squared raised to the 1/2. So let's get the derivative with respect to t. So power rule, move the 1/2 to the front. 1/2 times 13 plus 36t squared. 1/2 times minus 1, it's negative 1/2, but then times chain rule, times the derivative of the inside. The derivative of 13 is 0, but the derivative of 36t squared, multiply the 2 times the 36, that's 72t. Right? So the tangential component of acceleration is 72t times 1/2 will be 36t. And then that negative 1/2 power means over the square root of 13 plus 36t squared. But then we need to find the tangential component of acceleration when t is equal to 1. So I'm going to evaluate it when t is equal to 1. So it's going to be 36 times 1 divided by the square root of 13 plus 36 times 1 squared. So what do we get? It would be 36 over 13 plus 36, that would be 49. And the square root of 49 is 7, so it would be 36 over 7. 36/7. That would be the tangential component of acceleration. Okay? Now, remember that to find the normal component of acceleration, the formula would be the curvature times the magnitude of the velocity squared, but again, the curvature, it takes us a little long time to actually find it, so that's why we're going to use the Pythagorean theorem to find it at the end. So first I'm going to find the acceleration, okay? So to find the acceleration, remember that we need to go to the velocity and we need to get the derivative, right? So for the acceleration in respect to t, we need the derivative with respect to t of the velocity. So I want to get the derivative of this, and that would be the derivative of 3i would be 0i. The derivative of 2 would be 0j. And the derivative of 6t would be 6k. And then let's get the magnitude. Okay? That's what we need to do. But we need to find the acceleration at t equals 1. And since there is no t, it will be exactly the same thing. 0i plus 0j plus 6k. Then let's get the magnitude. Okay? The magnitude of the acceleration, it would be the square root of 0 squared plus 0 squared plus 6 squared. That would be the square root of 36, which is going to be 6. Now we need the tangential component of acceleration. The normal component of acceleration. To find it, we're going to do the Pythagorean theorem. It will be the square root of the hypotenuse, which is the acceleration, the magnitude of the acceleration square, minus the other leg, which is the magnitude of the tangential component of acceleration square. So the normal component of acceleration would be the same as the square root of 6 squared minus 36/7 squared. And that would give us the square root of 36 minus, if I square the 36/7, so let's see, 36 squared, that's going to give us 1,296. 1,296, 7 squared is 49. So we need to put this over 1 and multiply by 49 so we can have the same denominator. Right? So 36 times 49 gives us 1,764. So that equals to the square root of 1,764 49 minus 1,296 49, that is equal to minus 1,296 is 468 49. And I don't know, I believe the square root of 468, that's a perfect square. No. So 468, the only thing we can do is reduce it. I guess we can reduce it by 16, no, by 4. And that is a yes. Let me see if by 9. So it will be by 36. We can reduce it by 36. It would be the same as 36 times 13. So this is the same as the square root of 36 times the square root of 13. So that would be 6 times the square root of 13 over, and the square root of 49 is 7. 6 square root of 13 over 7. So let's write the acceleration in terms of t and n without finding the unit tangent or the unit normal. So the scalar, remember that the formula is the scalar, tangential component of acceleration times the unit tangent plus the normal component of acceleration times the unit normal. So that would give us the tangential component of acceleration was 36/7 times the unit tangent plus the normal component of acceleration is 6 square root of 13 over 7 times the unit normal. If we were to find the unit tangent and the unit normal as we regularly do, again, and then multiply times this component, we're going to get the exact same acceleration. Next problem. Let's do the same thing here. We want to write it also in the same form without finding t or n. Okay, let's do it. We need first of all to get the velocity, which is the same thing as the derivative with respect to t of the position. Okay. So the derivative would be 3t squared, the derivative is 6ti. The derivative of 3t would be 3, and the derivative of t cubed will be 3t squared. That is my j component, plus, and then the derivative of 3t is t, minus the derivative of t cubed will be 3t squared, and that is my k component. Now we need to get the magnitude of the velocity. So that will be the square root of, square the I component will be 36t squared, plus we're going to square this component, but I'm just going to write it like this for now, and we square them in a bit. And then also square this component. So that will give us the following. So 36t squared. Now right here we're going to do the square multiply square. Square the first term. So 3 squared is going to be 9. Plus multiply. 3 times 3 is 9. Times 2 is 18t squared. And then square the second component. 3t squared, if I square it, it's going to be a 9t to the 4th power. Then we're going to do the same thing to this guy. Square the first term. It will be 3 squared is 9. Then multiply 3 times negative 3 is negative 9 times 2 is negative 18 t squared. And then square the negative 3t squared. If I square negative 3t squared, we're going to get positive 9t to the 4th power. So the magnitude of the velocity is going to be as follows. Square root of, we can combine like terms. 36t squared minus 18t squared. Well, first of all, 9t to the 4th plus 9t to the 4th is 18t to the 4th. 36t squared minus 18t squared. Oh, well, 18 minus 18t squared, they cancel out right here. So we're going to end up with 36t squared plus 36t squared. And then 9 plus 9 would be plus 18. Okay, so what else can we do right here? Let me see if we can simplify it. We can actually factor. That's one thing that we could do right there to make it simpler. That's what I'm looking at. So if I factor the 18, we're going to be left with t to the 4th plus 2t squared plus 1. And then this is a perfect square trinomial. The factors of this trinomial will be t squared plus 1 and t squared plus 1. So this will be the same thing as the square root of 18 times t squared plus 1 squared. But the square root of t squared plus 1 squared would just be t squared plus 1, of course, making sure that this is positive, right? Times the square root of 18. Okay. And the square root of 18, we know the square root of 9 times 2. So that would be 3 square root of 2. So that would be the same as 3 square root of 2 times the absolute value of t squared plus 1. That would be the magnitude of the velocity. Okay. All right. So then remember that to find the tangential component of the acceleration, we need to find the derivative with respect, I'm going to first of all write it as we're looking for the tangential component of acceleration. That will be the derivative with respect to t of the magnitude of the velocity. Right? So let's get the derivative with respect to t of this right here. So we're going to get the derivative with respect to t of 3 square root of 2 times t squared plus 1. 3 square root of 2 times t squared plus 1. Okay, so the derivative of t squared plus 1 will be just 2t, right? So that would be 3 square root of 2 times 2t, and that will be the same as 6 times the square root of 2t. But then we want to find the tangential component of acceleration when t is equal to 1. So then evaluate it. So that will be 6 square root of 2 times 1. That would be 6 square root of 2. That is the tangential component of acceleration. Now, let's find the acceleration, because remember, for the normal component of acceleration, we need the curvature. But the curvature is a long way to find it. So I'm just going to get the acceleration of this particle. So that would be the derivative of the velocity, right? So we got the velocity right here. So the acceleration is going to be the same as the derivative with respect to t of the velocity, which we found up here. Okay, so the derivative of 6t would be 6, so it would be 6I plus the derivative of 3, 0. The derivative of 3t squared would be 6t, so it would be 6tj. And the derivative of 3, 0, the derivative of negative 3t squared is negative 60k. So but we want to find the acceleration when t is equal to 1. So that acceleration when t is equal to 1, oh, we need to get the magnitude. I forgot that. So before we work on this, or we can actually evaluate it and then find the magnitude. So when t is equal to 1, so that would be 6I plus 6 times 1, which is 6j, minus 6 times 1, which is minus 6k. So to get the magnitude of the acceleration, it would be the same as the square root of 6 squared plus 6 squared plus negative 6 squared. Okay, so that would be 36 plus 36 plus 36, so it would be basically the same thing as 3 times 36, right? Okay, and that is the same thing as 6 square root of 3, right? So that is the acceleration at t equals 1. But now we need to find the normal component of the acceleration. How do we find the normal component of the acceleration? With the Pythagorean theorem. So it will be the acceleration squared minus the tangential component of the acceleration squared. So the acceleration squared would be 6 square root of 3 squared minus the tangential component of the acceleration, which was, where was it? 6 square root of 2 squared. So square the components and then get the difference. We're going to get the square root of 6 squared is 36. Square root of 3 squared is 3. So it would be 36 times 3 minus 36 times 2. And that would be the same as 36 times 3 which is 108 minus 72. That will be the same as 36, and the square root of 36 is going to be 6. Summary. Write me the acceleration of this particle in terms of t and n without finding t and n, which is the unit tangent or the unit normal. So the formula is the tangential component of acceleration times the unit tangent plus the normal component of acceleration times the unit normal. And so the acceleration of this particle is tangential component of acceleration was 6 square root of 2 times the unit tangent plus the normal component of acceleration, which is 6 times the unit normal. Without finding the unit tangent and the unit normal, we get that the acceleration of this particle is given by this formula for whatever tangent, unit tangent, or whatever unit normal that particle gives us. Next, let's do the same thing here. Let's write A in this format again without finding t or n. Okay? When t is equal to 0. At the point that t is equal to 0, exactly. So, first of all, let's get the velocity, which is, remember, the derivative with respect to t of the position. So right here we need to use the product rule because it is a product. So it's the first times the derivative of the second. 8e to the t times the derivative of sine will be 8e to the t times cosine of t. Plus the second times the derivative of the first. The derivative of e to the t is still e to the t, right? So it will be just 8e to the t times sine of t. I. Now let's get the j component. Do the product also. the first times the derivative of the second, which is the derivative of cosine is negative sine. So that would be negative 8 e to the t sine of t plus the second times the derivative of the first. The derivative of e to the t is still e to the t. So it would be 8e to the t cosine of t. That's the j component. Plus, and the derivative of e to the t would just be e to the t. So that one stays as 8e to the t times the square root of 3k. That one doesn't change. Okay. So now we need to get the magnitude of the velocity. So the magnitude of the velocity, we're going to do the square root of the I component, which is 8e to the t cosine of t plus 8e to the t sine of t squared plus the j component, which is negative 8e to the t sine of t plus 8e to the t cosine of t squared plus, and then the k component. I'm going to move the square root of 3 to the front. That would be 8 square root of 3 times e to the t squared. Let's get that magnitude and see what it's going to come up to. We need to use the same thing we used on the previous problem. We need to square this binomial. So square the first term. So 8 squared would be 64. E to the t squared, it would be e to the 2t. And cosine squared would be cosine squared of t. Then multiply 8e to the t cosine of t times 8t to the t cosine of t times 2. 8 times 8 is 64 times 2 is going to be 128. E to the t times e to the t, it would be e to the 2t. And then cosine of t times sine of t would just be sine of t times cosine of t. Then plus the second term squared. So if I square this term, 8 squared, it's going to be 64. E to the t squared, it will be e to the 2t. And sine squared would be sine squared of t. Then we have to do the exact same thing to this guy. Square the first term. Negative 8 e to the t. If I square it, that's going to be positive 64. And then e to the t squared would be e to the 2t. And then sine squared would be sine squared of t. Then multiply. Negative 8 times 8 is negative 64. Times 2 is negative 128. E to the t times e to the t, it would be e to the 2t. Then sine of t times cosine of t, it would just be sine of t times cosine of t. Then plus square of the second term. 8 squared would be 64. E to the t squared would be e to the 2t. And cosine of t would be cosine squared would be cosine squared of t. And last, square this last term. 8 squared would be 64. Square root of 3 squared would be 3. So 64, just multiply 64 times 3. And that would give you 192. So it would be plus 192. E to the t squared would be e to the 2t. Let's go ahead and combine like terms. Now I want you to notice something here. 128 e to the 2t sine of t cosine of t minus 128 e to the 2t sine of t cosine of t, they cancel out. What else? I don't think anything else cancels, right? 64 e to the 2t cosine of t. Let's see, do we have any like terms? Yes. 64 e to the 2t cosine square of t plus 64 e to the 2t cosine square of t. That would be 128 e to the 2t cosine square of t. Then what else can we combine? 64 e to the 2t sine square of t plus 64 e to the 2t sine square of t would be plus 128 e to the 2t sine square of t. And what else do we have? The last term, which is plus the 192 e to the 2t. What else can we do? We can factor, as you can see. For the next thing, we can factor 64. Yeah, so we can factor a 64 e to the 2t. Yeah. So if we factor the 64 e to the 2t, we're left with 2 cosine square of t. You know what? Before I do that, I'm gonna do it something different for one reason. I want you to look first at the sine square and cosine square, because you know what's gonna happen there. Okay? So from those two, I'm gonna factor the 128 e to the 2t. And if I factor it, then we're left with cosine square of t plus sine square of t, which you know what happens there. That is equal to 1. And then plus the 192 e to the 2t. So when I multiply the 1 times 128 e to the 2t, that leaves us with 128 e to the 2t plus the 192 e to the 2t. Oops. When I add them, let's just add them really quick. So 128 plus 192, that's going to be 320. So that would be the same as the square root of 320 e to the 2t. And 320 doesn't have a perfect square, but we can factor it. Let me see. Is it by 64? Yes. 64 and 5. Okay? So the square root of 64 is 8, and the square root of e to the 2t is just e to the t. So this is the same as 8 e to the t times the square root of the 5. Or 8 square root of 5 times e to the t, which is the same. Okay? So we're very close. So now to get the tangential component of acceleration, we need to get the derivative with respect to t of the magnitude of the velocity. So we need to get the derivative with respect to t of this guy that we just found, which is 8. I'm just going to put the square root of 5 here. 8 square root of 5 times e to the t. If I get the derivative with respect to t, the derivative of e to the t is just e to the t. So it's going to stay the same. 8 square root of 5 e to the t. But then we want to find the acceleration at t equals to 0. So that's the next thing we need to do. So we're going to evaluate it at t equals 0. So that would be 8 square root of 5 times e raised to the 0 power would just be 8 square root of 5. Because e to the 0 is just 1. Alright, so how can we get the normal component of acceleration without having to find the curvature? We need to find first the acceleration at t equals 1, the acceleration of the curve at t equals 1. So we need to find the derivative of the velocity to find the acceleration. So that's what we're going to do next. Get the derivative of that velocity to find the acceleration. So right here, let's see, I think we can see it, yeah? So acceleration with respect to t, derivative with respect to t, let me put it a little bit higher so I don't have to scroll down, the derivative with respect to t of that velocity. Okay, so right here the derivative of, we have to do a lot of stuff, we have to do a lot of products. So because this is a product, this is a product. So that's going to be a long equation. So bear with me. The first times the derivative of the second. The derivative of cosine is negative sine. So it would be negative 8 e to the t sine of t. Plus the second times the derivative of the first. The derivative of 8e to the t would be 8e to the t. So that stays the same. 8e to the t cosine of t. Now the second one is also a product. The first one times the derivative of the second. The derivative of sine of t would be cosine of t. So it would be 8 e to the t cosine of t plus the second times the derivative of the first. The derivative of 8e to the t would just be 8e to the t. So it's 8e to the t times sine of t. And this is just the I component. But guess what? If you notice, negative 8e to the t sine of t plus 8e to the t sine of t, they cancel. And 8e to the t cosine of t plus 8e to the t cosine of t would just be 16e to the t cosine of t. And this is the I component of the acceleration. Okay, now let's continue with the j component of the acceleration. Let's continue right here. We're going to do several products also. It would be, right here this is a product, so it will be the first times the derivative of the second. So the derivative of sine is cosine, so it will be negative 8e to the t times cosine of t. Plus the second times the derivative of the first. The derivative of negative 8e to the t is just negative 8e to the t. So it's going to stay as minus 8e to the t sine of t. Then for the next one, we need to do the first one times the derivative of the second. The derivative of cosine is negative sine. So it would be negative 8e to the t sine of t. Plus the second times the derivative of the first. The derivative of 8e to the t is just 8e to the t times cosine of t. That would be the j component. And then plus the derivative of 8e to the t square root of 3. E to the t, the derivative is still e to the t, so it just stays as 8e to the t times the square root of 3k. What can we simplify right here, as you can see? Negative 8e to the t cosine of t plus 8e to the t cosine of t, they cancel. Then, negative 8e to the t sine of t minus 8e to the t sine of t would be minus 16. Or we can say plus negative 16 e to the t sine of t. And that is my j component. And then we said that the k component was plus 8 e, I can put the square root of 3 in the front if you want. 8 square root of 3 times e to the t k. We're very close. Now we need to find the acceleration at t equals 2. We said what? 0, right? So let's find the acceleration at t equals 0. Okay. So that would be 16 times e to the 0 cosine of 0 I plus negative 16 times e to the 0 sine of 0 j plus 8 square root of 3 times e to the 0 k. Let's see what that's going to give us. The acceleration at t equals 0 is going to be e to the 0 is 1, cosine of 0 is 1, so 16 times 1 times 1 is 16i. E to the 0 is 1, but sine of 0 is 0, so 0 times 1 times negative 16 is going to be 0j. E to the 0 is 1 times 8 square root of 3 would be plus 8 square root of 3k. Okay? Now, to find the magnitude of the acceleration at t equals 0, then we need to get the square root of 16 squared plus 0 squared plus 8 square root of 3 squared. So that would be 256, the square root of 256, plus 8 squared is 64. 64 times 3 is 192. So then when we add, hold on. Alright, when we add 256 plus 192, that gives us 448. Oh, and I think this is a good one, because the square root of 448, the square root of 448 is actually, no, not a perfect square. I thought it was 441. That's what I was thinking. So I need to simplify it. So let's reduce it by, I believe, by 64. Yeah, so 64 and 7. So that would be the square root of 64 times the square root of 7. So that would be 8 square root of 7. That's the acceleration. But I need the normal component of acceleration. So to find the normal component of acceleration, that would be the same as the square root of the acceleration square minus the tangential component of the acceleration square at that t equals 0. So then the normal component of acceleration is going to be the same as the square root of the acceleration square, which is 8 square root of 7 square minus the tangential component of acceleration that we found it to be 8 square root of 5. That's what we found the tangential component of acceleration to be. 8 square root of 5 minus 8 square root of 5 square. And let's find the normal component of acceleration. So it would be 64 times 7. 64 times 7, which is 448. Minus 64 times 5, which is 320. Right? So that would be 128. But the square root of 128 will be 64 times square root of 64 times square root of 2, which is 8 square root of 2. So let's write the acceleration in terms of the tangential component of acceleration times the unit tangent plus the normal component of acceleration times the unit normal. So tangential component of the tangential component of acceleration was found to be we said 8 square root of 5, I believe so, times the unit tangent plus the normal component of acceleration was 8 square root of 2 times the unit normal. Without finding t or n, which in this problem it was going to be even way longer than this, we found the acceleration of the particle when t is equal to 0 in terms of the unit tangent and the unit normal. Okay. Next question. Okay. On this one, we are going to basically do the same thing, but on this one we're going to find additional things, which is finding the osculating, normal, and rectifying planes for the particle that is moving in space at this position, using this position vector. Okay. So first of all, well, I think we can find the position. The position at t equals to pi over 3, we can find it by just replacing it into the position function. So that is the first thing we should do. So the initial position of the particle would be cosine of pi over 3i plus then plus sine of pi over 3 j minus 2k. That one does not have a t, so it's just 2k. It's a constant. So the initial position, or the position at pi over 3, is going to be as follows. Cosine of pi over 3 is equal to 1/2, so it will be 1/2 I, plus sine of pi over 3 would be square root of 3 over 2 j minus 2k. So we can say that the initial the position at pi over 3 would be the point 1/2 comma square root of 3 over 2 comma negative 2. This is the position at t equals pi over 3. I'm writing it in this form because in order for us to get the equation of the planes, like osculating, normal, and rectifying planes, we need a point to find the equations of the plane. So that's why I got the plane at this position. Alright, so, and this is one of the answers that we needed, the position at pi over 3, that was r. Now we need to get the tangent vector, the normal vector, and the binormal vector. So remember that to get the unit tangent, we need to get the derivative of the position and divide it by its magnitude. So derivative of cosine would be negative sine of t I. Derivative of sine would be cosine of t j, and the derivative of negative 2 would be 0. So it would be plus, I'm just going to put plus 0 k. Then we need to get the magnitude. So if I square the sine, it would be sine square of t. If I square the cosine, it would be cosine square of t. And then if I square the 0, I still get 0. So that gives me sine square plus cosine square. But sine square plus cosine square is going to be equal to 1. So the square root of 1 is going to give me a 1. And it makes sense because cosine square plus sine square, remember that creates a particle moving along a unit circle. We talked about that in previous sections. So then the unit tangent vector, we divide the vector divided by its magnitude, the derivative of the position divided by its magnitude. If I divide these components by 1, it's just going to be the same. Negative sine of t I plus cosine of t j plus 0k. But we want to find the tangent vector at the position pi over 3 when t is equal to pi over 3. So we evaluated negative sine of pi over 3i plus cosine of pi over 3j plus 0k gives us the unit tangent vector. Sine of pi over 3, we said it was the square root of 3 over 2, but it's negative right there. So negative square root of 3 over 2i. Cosine of pi over 3, it's 1/2, so it will be plus 1/2 j plus 0k. This will be the tangent vector at the point pi over 3. T equals pi over 3. Next, now we need to find the normal vector. Now, to be able to find the normal vector, we need to find the derivative of this tangent vector. Okay? So we need to get the derivative of the tangent vector and divide it by its magnitude. So we're looking at this guy, and we're going to find its derivative. The derivative of negative sine of t would be negative cosine of t. I. The derivative of cosine of t would be negative sine of t. J. And the derivative of 0 would be 0 still. Right? And then I need to find the magnitude. So the magnitude, I find it the same way. So it would be, you already know what the magnitude is going to be. Since this is a unit circle, then the magnitude has to be 1. So when I square the cosine, it would be cosine square of t. When I square the sine, it would be sine square of t. When I square the 0, it will still be 0 squared. It will be 0. So that will give me cosine square plus sine square, which is still 1, or sine square plus cosine square, which is still 1. So when I divide the derivative of the tangent by its magnitude, that is going to give us the normal vector. So if I divide this by 1, it's still going to give me the same thing, which is negative cosine of ti plus negative sine of tj plus 0k. And we want to find the normal when t equals to pi over 3. Let's evaluate it. So that will be negative cosine of pi over 3I plus negative sine of pi over 3j plus 0k. So the normal at pi over 3 is going to be cosine of pi over 3 is 1/2, so that will be negative 1/2 I. Sine of pi over 3 is the square root of 3 over 2, so it will be minus the square root of 3 over 2j plus 0k. This is the normal vector that we're going to have, or the perpendicular vector to the plane, or to the particle moving along the curve r sub t at the instant that it's at t equals to pi over 3. Next one. Now we are going to be finding the binormal vector. This is a new one to our list of vectors. To find the binormal vector, we need to use the cross product of the tangent vector and the normal vector, which we do it with the determinant form, remember. I'm going to separate this a little bit. So, the tangent vector, let's take a look at the unit tangent. It was negative sine of t, cosine of t, and 0. Negative sine of t, cosine of t, and 0. And then the normal vector that we found was negative cosine of t, negative sine of t, and 0. And then let's do the determinant. It would be I times the determinant of these 4 right here, which is cosine of t, 0, negative sine of t, and 0. Then minus j times the determinant of these 4, which is negative sine of t, 0, negative cosine of t, and 0. And then the plus k times the determinant of these 4, which is negative sine of t, cosine of t, negative cosine of t, and negative sine of t. That's going to give us the binormal vector, which is normal to both the tangent and the normal. So, right here, this is going to give us a 0, right? So it will be 0i. This right here is also going to give us a 0, so it will be plus 0j. The only one that will not be 0 is the k. So it would be negative sine of t times negative sine of t would be positive sine square of t, minus negative cosine of t times cosine of t would be negative cosine square of t. That would be my k component. That gives me sine square plus cosine square, which is, again, 1. So the binormal vector is going to be 0i plus 0j plus 1k. Okay? But I want to find the binormal vector at pi over 3. Guess what? It's still the same because there is no t anymore. Right? 0i plus 0j plus k. That's the binormal vector at the instant that is at pi over 3. So we found the first 4 answers there. Now we want to find the equations for the osculating planes, normal plane, and rectifying planes. Let's start with the osculating plane. So the osculating plane, remember that is normal to the binormal plane. To binormal vector, I'm sorry. Since it is normal to the binormal vector, then that means that the components of the binormal vector will be the same as the components of the plane. What do I mean by the components of the plane? Remember, this is the equation of the plane. Ax minus x of 0 plus b times y minus y of 0 plus c times z minus z of 0 equals to 0. This is the component form, right? And we know the x of 0, y of 0, and z of 0. That is the initial position, or the position of the particle. And that's what we found at the beginning. What's the position of the particle at pi over 3? 1/2 square root of 3 over 2 and negative 2. So my is 1/2 square root of 3 over 2 and negative 2. That is my initial position, x of 0, y of 0, and z of 0. And the components of the plane A, B, and C would be the same as the components of the binormal, because that binormal is normal to the osculating plane, meaning that the components of this plane will be the same as the components of the plane. It would be 0 times x minus 1/2 plus 0 times y minus the square root of 3 over 2 plus, then the c, it's a 1, that's the value of k, times z minus negative 2. That's going to be a plus 2. So all of these become 0, so all we're going to have is z plus 2 equals to 0. So the equation of the osculating plane would just be the plane z equals negative 2. That's the equation of the osculating plane. Now let's find the equation of the rectifying plane. The rectifying plane is the one that goes in the direction of the tangent, of the tangent vector, that plane. And the rectifying plane, remember, that is normal to the normal vector. Okay? Since it is normal to the normal vector, that means that the components of the normal vector, which is this guy, these three components will be the A, B, C components of that plane. So let's go ahead and set it up. A times x minus x of 0 plus b times y minus y of 0 plus c times z minus z of 0 equals to 0. So the components of the normal plane are negative 1/2, that is my A component, times x minus, and the x of 0 is 1/2, we found it here on the position at the beginning, plus the B component, which is the J component, is negative square root of 3 over 2. So negative square root of 3 over 2 times y minus y of 0, which is the square root of 3 over 2, plus the C component, which is the K component of the normal, is 0. So it will be 0 times z minus z of 0, which is negative 2, equals to 0. So it changes to a plus. And then we're going to distribute. Negative 1/2 times x is negative 1/2 x. Negative 1/2 times negative 1/2 is positive 1/4. Negative square root of 3 over 2 times y is negative square root of 3 over 2y. Negative square root of 3 over 2 times negative square root of 3 over 2 is positive 3 over 4. Plus, and then 0 times any of that is just going to be 0, so I don't have to do anything there, so that's just 0, equals to 0. Then combine like terms. One-fourth plus 3/4, it's going to be 4/4, which is 1. So move the 1 over to the other side. So the equation of the rectifying plane is negative 1/2 x minus the square root of 3 over 2y equals negative 1. That's the equation of the rectifying plane. Now we need the normal plane. Normal. The normal plane is normal to the tangent vector. So since it is normal to the tangent vector, then the components of the tangent vector will be the same as the ABC components of the plane. So these are the components of that plane. So I'm going to start by setting it up as this. A times x minus x of 0 plus b times y minus y of 0 plus c times z minus z of 0 equals to 0. And so the a component, which is the I component of the tangent plane, is negative square root of 3 over 2. X minus, and the x of 0 is 1/2. Is the same, is the standard position. Plus, and then the b component, which is the j component, is 1/2. So it will be 1/2 times y minus y of 0, which is the square root of 3 over 2. Plus, and then the c, I believe it was 0. Yeah, 0, that's the c component, times z minus z of 0, which is negative 2, equals to 0. That changes to an addition, but anyhow, that's just 0. Okay? Negative square root of 3 over 2 times x is negative square root of 3 over 2x. Negative square root of 3 over 2 times negative 1/2 is positive square root of 3 over 4. Plus 1/2 times y is 1/2 y. 1/2 times negative square root of 3 over 2 is negative square root of 3 over 4. Then this is 0, so that's equal to 0. Square root of 3 over 4 minus square root of 3 over 4, they cancel, so we're left with negative square root of 3 over 2x plus 1/2 y equals to 0. And this is the equation of the normal plane. You can sketch them just to give you an idea of how the particle is moving in space. Those planes are basically what they tell you. They give you a better idea. And also the normal vector, the tangent vector, and the binormal vector. They give you an idea in the direction of which the given particle, r of t, is traveling along the space curve. Alrighty. So we're going to answer one more question, which is going to be this. We have an object of mass m that is traveling along the parabola y equals x squared with a constant speed of 9 units per second. What is the force on the object due to its acceleration at the point, at the instant that is located in the position 6 raised to the 1/2 power, comma 6. So to find the force, remember the formula for newtons is force equals mass times acceleration. We're going to leave it in terms of the mass because it just tells me for any general body of mass m. So for whatever mass is going to follow the same path for the force vector. So we're just going to leave it in terms of m. Alright, so what is it that we need? We need the acceleration in order for us to find that, the force. Now, to find the acceleration, first of all, we need the position, but to find the position, we need to write a parametric equations that will give me a particle moving along that parabola y equals x squared. The easiest way to find the parametric equations is this. We can say that x is equal to t. We can just let the x be t, and so the y is going to be equal to x squared, but x we said it was t, so it would be t squared. And remember that if I want to write it in terms of a vector, then the x will be my I component, so it will be ti, plus, and the y will be my j component, so it will be t squared j. So, to find the acceleration, we need the velocity, which is the derivative of the position. Find the derivative. So it would be I plus 2tj. Before I continue, let's see how far we need to get to be able to find the acceleration. Remember that the acceleration, according to this section, is the tangential component of the acceleration times the tangent vector, sometimes the unit tangent, plus the normal component of the acceleration times the unit normal. So we need to find the tangential component, the normal component, and in this case, we want the equation by finding t and n. Like right here, we cannot deviate from that because we want to find the exact force in terms of a vector, not in terms of t and n. I want them just in terms of I, j, and k. Okay, so we're going to be finding t, we're going to be finding n, which is a unit tangent, unit normal, and then the tangential component of acceleration and the normal component of acceleration. So, to find the tangential component of acceleration, this is the velocity. I need to find the magnitude of the velocity first, remember? That would be 1 square plus the square of this one, it would be 4t squared. And then we need to get to find the tangential component of acceleration. We need to find the derivative. The derivative of the magnitude of the velocity with respect to t. So that would just be the square root of 1 plus 4t squared. So if I get the derivative, then that's a 1/2 power, remember? So it would be the same as finding the derivative with respect to t of 1 plus 4t squared raised to the 1/2. So let's use the power rule. Move the 1/2 over, so that's 1/2 times 1 plus 4t squared, and then subtract 1, so that's minus negative 1/2, times the derivative of the inside. The derivative of 1 is 0, the derivative of 4t squared would be 8t. Then that's going to give us 1/2 times 8t would be 4t over, now that negative 1/2 means this on the bottom, the square root of 1 plus 4t squared. Okay. So that's the tangential component of the acceleration. Hold on a second. Actually, for the tangential component of acceleration, we don't need to find the... We're going to use this, of course, later. But I don't need to find the derivative of the magnitude of the velocity, because it tells me that an object of mass m travels along the parabola y equals x squared with a constant speed of 9 units per second. So the magnitude of the velocity is 9. So they already give it to me. So that's the magnitude of the velocity. So we can go back here, and again, that's fine that we found the magnitude of the velocity because we're going to use it for the unit tangent, remember. Because that magnitude of velocity is the magnitude of the derivative of the position, right? So we're going to use that right now. So to find the tangential component of acceleration is the derivative of the derivative of the magnitude of the velocity, which in this case is the derivative with respect to t of 9, because that's the velocity, that's the speed. And the derivative with respect to t of 9, since it doesn't have t, then it would just be 0. So that's the tangential component of acceleration. Now, how do we find the acceleration? We just continue working it out. This is the position, the derivative of the position, which is the velocity. I just get the derivative of the velocity to get the acceleration. So, I'm going to find the acceleration. So the acceleration is going to be the derivative with respect to t of the velocity. Or we can say of the derivative of the position, which is the velocity, right? So the derivative of this guy, the derivative of 1 is 0, so it would be 0i. The derivative of 2t would just be 2, so it would be 2j. And then if I want to get the magnitude, right here, it doesn't matter at what value of t, you see it's a constant acceleration, right? Because it says that it's a constant speed, so it's not really accelerating. So the acceleration it's constant. So what is the acceleration right here? So we get the magnitude of the acceleration by getting the square root of 0 squared plus 2 squared. So it's going to be the square root of 4, which is 2. So it is just going at this same acceleration. It is not accelerating or decelerating. This is the constant, okay, acceleration here of 2. So we can find also the unit normal vector. Let's see. Okay, never mind. We need to find the acceleration. I don't know why I went to find this last piece. That's what I'm looking for, the acceleration function. Okay, so that a is what we're looking for. So it's not going to be a constant. It's going to be a vector function. Now, we need to find the normal component of acceleration, but unfortunately, we cannot do the Pythagorean theorem because this is not, we don't know what this acceleration function is going to be. So what I'm going to do is I'm going to use the original formula for the normal component of acceleration that was introduced, which is the curvature times the magnitude of the velocity squared. I think this is the best we can use because we're given the magnitude of the velocity. So I'm going to use the original formula that we were given in this case because we're given the constant velocity. So this way we have to work it out differently. So the acceleration equals to the tangential component of acceleration, which is 0 times the unit tangent vector plus the curvature, which we don't know what it is, times the velocity, which is 9 units per second squared times the normal unit vector. So the acceleration will be 0 times the tangent times the unit tangent plus 81 times the curvature times the unit normal vector. So in this case, since this is 0, we're not actually the acceleration is not going to depend on the tangent component. It's just going to depend on the normal component. It is just going to be that. So it is always going to be just the normal component. So in this case, the acceleration is going to be given by 81 times the curvature times the normal unit normal vector. Okay, that's what we're going to use to find the acceleration. So what do we need next? We need to find the normal vector and we need to find the curvature. Those are the two things we need to find next. So first of all, we can define the tangent. We need to go in pieces. To write the tangent, we divide the derivative of the position divided by its magnitude. That's the formula to find the tangent vector. So the derivative of the position is this, and the magnitude was this. So it's going to be 1 divided by this. So 1 divided by the square root of 1 plus 4t squared, I, plus then the j component, which is 2t, divided by the magnitude, which is the square root of 1 plus 4t squared, and that is j. Next. Now we need to be able to find the curvature, we need the magnitude of the derivative of the tangent and then its magnitude. So to get the derivative of the tangent, I would recommend we use the product rule formula because this is a quotient and it's going to be longer. So what I'm going to do first, I'm going to modify it and make it a product by moving the radical to the top as a negative 1/2 power. So that would be the same as 1 plus 4t squared, the 1 I don't need to put it, raised to the negative 1/2 I plus 2t times 1 plus 4t squared raised to the negative 1/2, and that's the j. Let's get the derivative. Power rule. Negative 1/2 goes to the front, times 1 plus 4t squared, and then negative 1/2 minus 1 is negative 3/2, times the derivative of the inside, which is the chain rule. Derivative of 1 is 0, derivative of 4t squared would be 8t. That would be my I component. Plus, right here we need to use the product rule. It would be the first, which is 2t, times the derivative of the second. The derivative of this, we move the negative 1/2 to the front, times 1 plus 4t squared. Negative 1/2 minus 1 is negative 3/2. Plus, times the derivative of the inside. The derivative of the inside is 8t. And then plus the second times the derivative of the first. The derivative of 2t is going to be 2 times 1 plus 4t squared raised to the negative 1/2. This is my j component. Let's continue. So the derivative of the unit tangent is going to be 8t times negative 1/2 is negative 4t. And that 3/2, negative 3/2 means on the bottom 1 plus 4t squared raised to the positive 3/2. And that is the I component. Plus, let's find the j component. 2t times negative 1/2 would be negative t. Oh, I forgot one thing. 2t times negative 1/2 is negative t. Negative t times 8t is negative 8t squared. So, and that negative 3/2 power means over the 1 plus 4t squared raised to the positive 3/2. And then plus 2, and then the negative 1/2 power means 2 over 1 plus 4t squared raised to the positive 1/2. And that would be the j component. Right here we need to have the same denominator, so to make this 1/2 a 3/2, I need to multiply by 1 plus 4t squared on both the numerator and denominator. And that would give us the derivative of the unit tangent, which is going to be negative 4t over 1 plus 4t squared raised to the 3/2 power I, plus when we distribute that to the top, we get negative 8t squared. 2 times 1 is going to be plus 2. 2 times 4t squared is going to be plus 8t squared over the denominator 1 plus 4t squared raised to the 3/2. J. And look what happens. The negative 8t squared, positive 8t squared cancel, so we're just left with this. Negative 4t over 1 plus 4t squared raised to the 3/2. This is my I component. Plus 2 over 1 plus 4t squared to the 3/2. This is the j component. Alright, so now we need to find the magnitude of this unit, of this derivative of the tangent vector. So the magnitude, we get it by the square root of, square the 4t would be 16t squared. Everything is over the same denominator, so I'm just going to put it over the same line. Plus, square the 2, that's going to be 4. And on the bottom, if I square, the 2 on the denominator is going to disappear. So there's 1 plus 4t squared raised to the 3rd power. But then you see that we can factor a 4 from the numerator, and that leaves us with 4t squared plus 1, which is the same thing as the 1 plus 4t squared at the bottom. So we can simplify one of these with one of these, so we're left with 2 on the bottom. So that leaves us with the square root of 4 over 1 plus 4t squared raised to the 2nd power. The square root of 4 is 2, and the square root of 1 plus 4t squared is going to be just 1 plus 4t squared. Alright, so Right, so what next? So we need to find the curvature. The curvature, if you remember, we find it by dividing the derivative of the unit tangent vector divided by the magnitude of the derivative of the unit tangent vector divided by the magnitude of the derivative of the position vector. So it is going to be this, which is the magnitude of the derivative of the unit tangent, divided by the magnitude of the derivative of the position, which we found that right here, square root of 1 plus 4t squared. And that's over 1, right? So we're going to multiply by the reciprocal. So times 1 over the square root of 1 plus 4t squared. But that, when I multiply this by itself, I just add the exponents. It would be 1 plus 1/2. It's going to be 3/2. So we're going to have 2 over 1 plus 4t squared raised to the 3/2 power. And this gives us the curvature. Okay. All right. Now we need the normal unit, the principal normal unit vector. To find that, we need to divide the derivative of the tangent vector divided by its magnitude. Okay. So the derivative of the tangent vector, it is right here, I and j, and we're going to divide it by the magnitude, which is this right here. So we're going to start with the I component. Negative 4t over 1 plus 4t squared to the 3/2. And that we're going to divide it by its magnitude, which is 2 over 1 plus 4t squared. And this is going to be my I component. Plus, now let's do the j component. We're going to have the j component, which is 2 over 1 plus 4t squared raised to the 3/2 power, and then divided by the magnitude, which is 2 over 1 plus 4t squared. And this is the j component of the normal unit vector. So my normal unit vector is therefore going to be multiplied by the reciprocal. So it's negative 4t over 1 plus 4t squared to the 3/2 multiply times 1 plus 4t squared divided by 2. This is going to give us the I component, plus then multiply by the reciprocal here is 2 over 1 plus 4t squared raised to the 3/2 times the reciprocal, which is 1 plus 4t squared divided by 2. That's the j component. So the unit normal vector is therefore going to be negative 4t divided by 2, it's going to be negative 2t. This can be reduced right here, so it's going to be negative 2t. Right? Then, I can simplify the 1 plus 4t squared with 1 of the 1 plus 4t squared right here, and that leaves us with 1/2, because this is 1 1/2, right? So I just reduce one of them. Right here, I can reduce these 2's, and I can reduce one of these, 1 plus 4t squared with 1 plus 4t squared, and that leaves me with the 1/2 on this one. So the unit normal vector is going to be negative 2t over 1 plus 4t squared to the 1/2 is going to be the same as the square root of 1 plus 4t squared. That is my I component, plus, and then on the j component, there's nothing left on the top, so we're going to have a 1 over, and then 1 plus 4t squared to the 1/2 means the square root of 1 plus 4t squared. And that's the j component. So, now let's go back to the formula. To find the acceleration, we need, it was the 0 times the, remember we found the tangential component of the acceleration was 0 times the unit tangent plus, we don't know what the normal vector or the normal vector of acceleration is. So we said that we could use the formula. It was the curvature times the velocity square times the normal vector. But the velocity square, we said it was 81, so we said it was 81 times the curvature times the normal vector. So we don't need the 0 times the unit tangent because that's just going to be 0. So the acceleration of this particle is going to be given by 81 times the curvature. But what was the curvature that we found? 2 over 1 plus 4t squared raised to the 3/2 power. Okay. 2 over 1 plus 4t squared raised to the 3/2 power. Wait a second. I'm just looking at... Oh, no, I was right there. Yeah. Okay. I was looking at something else. So let's put it 2 over 1 plus 4t squared raised to the 3/2 power. I'm going to leave some space here. Raised to the 3/2 power. And we're going to multiply this times the normal vector. The normal vector is negative 2t over the square root. Instead of the square root, I'm just going to put it as 1/2 power. Okay, 1 plus 4t squared to the 1/2 I plus 1 over 1 plus 4t squared raised to the 1/2 j. If I distribute this, what's going to happen? And also the 81. 81 times 2 is 162. Right? So the acceleration is going to be 162. 162 times negative 2t would be negative 324. Yeah? Is that correct? Yes, right. Alright, so negative 324, and then we have t, right? Then over, when I multiply this by itself, I just add the exponents. 3/2 plus 1/2 is going to be 4/2, which is the same as 2. So that would give me 1 plus 4t squared raised to the 2nd power. This is the I component of the acceleration, plus 1 over, well, not 1. Distribute 162 times 1, it's going to be 162 over, when I distribute this by this, then add the exponent, so that would be the same as 1 plus 4t squared raised to the 2nd power, j. Okay, and this so far gives us the acceleration of the particle at any value of t. Now it is time to do our substitutions, because we want to find, first of all, we want to find the force, but we want to find the force due to acceleration at this particular point in time. So when t is equal to 6 and 6 raised to the 1/2 power. So we're going to replace the t with the 6 to the 1/2 power. That would be the next thing to do. To first find the acceleration when t is equal to 6 to the 1/2. So that's negative 324 times 6 raised to the 1/2 power divided by 1 plus 4 times 6 raised to the 1/2 power squared. And then that is going to be squared right here. That will be the I component plus 162 divided by 1 plus 4 times 6 raised to the 1/2 power squared, and if that is being squared, and that is the j component. So the acceleration is going to be 6 to the 1/2 means the square root of 6. So that's negative 324 square root of 6 over, now right here let's evaluate it. That's just going to cancel, simplify. That's going to be 6 times 4 is 24 plus 1 is 25, and 25 squared. 25 squared, it's going to be 625. So that's what we're going to get right here, divided by 625. I plus 162 over, now this is also going to be a 625 over 625J. This is the acceleration of the particle that is traveling along the parabola at the instant, that is at the location t equals to 6 to raise to the 1/2, comma 6. That is the acceleration. But now I want you to give me, okay, then if this is the acceleration, what is the force that is applying or exerting along the parabola at that instant? And force is equal to mass times acceleration. All we need to do, since this doesn't give me like any specific mass, basically we're just going to leave it in terms of the letter m as the mass. So it's just going to be the same as negative 324 square root of 6 over 625 m, and this is my I component, plus 162 over 625 m, and this is my J component. So, reading the problem, what is the force on the object due to its acceleration at the location 6 raised to the 1/2, comma 6? The force of the object on the parabola y equals x squared at 6 raised to the 1/2, comma 6 is negative 324 square root of 6 over 625 times the mass I plus 162 over 625 times the mass J. Okay. And this completes section 12.5.